Hey everyone, welcome to this explainer. Today we have an absolutely fascinating journey ahead of us as we unpack the invisible architecture powering the modern web. We're going to demystify exactly how today's databases handle truly massive scale. If you've ever found yourself wondering how platforms can manage billions of active users without just completely crashing, or how your data gets distributed across the globe in milliseconds, well, you are in the exact right place. We're going to decode the core concepts of big data storage, specifically zoning in on the base principle and the massive NoSQL revolution. All right, so here is our roadmap for today. First up, we'll hit the big data problem. Number 2, we'll break down the base principle. 3, we'll enter the NoSQL era. And finally, number 4, we'll look at the 4 types of NoSQL. Let's dive right in. Section 1. The big data problem, and the real challenges of massive scale. To really understand why our storage methods had to evolve so drastically, we kind of have to ask, how exactly did we get here? Think back to the early internet boom. Almost overnight, we had social media giants like Facebook and Twitter generating these unimaginable, nonstop streams of data. Right alongside that, we saw the explosive rise of cloud-based solutions, think Amazon S3, giving us the actual infrastructure to store it all. But honestly, the real kicker was the shift in the data itself. Just as developers were moving to dynamically typed programming languages, the data became dynamically typed too. We were suddenly dealing with continuous schema evolution. The shape and structure of data was just constantly changing on the fly. And man, did this create a huge friction point. On one hand, you had traditional relational database management systems, or RDBMS. Picture an RDBMS as a really strict no-nonsense librarian. It completely assumes your data is dense, uniform, and fits perfectly into neat little rows and columns. But the reality of big data coming from the internet? It's the complete opposite. It's impossibly massive, it's sparse, and it's largely unstructured. When you try to force that chaotic reality into rigid traditional systems, you literally stretch them to the breaking point. Moving right along to Section 2, the base principle, and how it completely changed database design. To solve the huge scaling nightmare we just talked about, engineers had to totally flip their mindset. And that led to a database design principle known as BASE. Let's quickly dejargonize this. BASE stands for Basically Available, Soft State and Eventual Consistency. It's heavily leveraged by modern distributed systems. But the absolute crucial takeaway here is this. When a system uses BASE, it actively favors availability over consistency. In a world that literally never sleeps, making sure the database is up and responding is way more important than making sure every single server on Earth has the exact same data at the exact same millisecond. Take a look at how this brilliantly plays out during a crisis. Here you have a distributed system that suffered a total network failure. It's split into partition A and partition B. But because the system is basically available, if a user makes a request, the database will always acknowledge it. It'll grab whatever data it can from reachable peers, or at least give you a quick success or failure notification. It doesn't just completely freeze up and die just because one part of the network went dark. Then we have this super interesting concept of a soft state. Since we are prioritizing keeping the system running no matter what, the database might actually be in a temporary inconsistent state. Imagine user A updates a record. If user B asks for that exact same record a millisecond later, before the update has traveled across the network, well, because it's a soft state, the database might actually return stale, outdated data to user B. The reality is, if they hit refresh 2 seconds later, the result would probably change. Which naturally brings us right to eventual consistency. The system isn't going to stay out of sync forever. Think of it like swapping out your profile pic on a massive app. You update the picture, your friend looks at your profile a second later and still sees the old picture. That's the soft state in action, pulling from a server that hasn't caught up yet. But eventually, that change ripples across all the global nodes. Consistency is attained, and another friend who checks a few minutes later gets the fully updated picture. Let's move to Section 3, entering the NoSQL era, the rise of next-gen databases. Okay, so BASE gave us the theory, but NoSQL gave us the practical tools. But what does it actually mean? It stands for no relational, no RDBMS, or honestly, my personal favorite, not only SQL. It's really just a massive umbrella term for an entire class of data stores that look at those strict old-school RDBMS rules and say, yeah, no thanks. When your datasets explode into the terabytes and you desperately need fault tolerance and insanely parallel processing, NoSQL is the toolkit you grab. To really ground this, let's look at how the folks at NoSQLdatabase.org defined it back during the rapid growth phase of 2009. They basically called these next-generation databases custom-built for web scale. Pay attention to the keywords here: non-relational, distributed, and horizontally scalable. Plus, they are schema-free, they run on simple APIs, and they are built entirely on that eventually consistent base principle we just mastered. And finally, Section 4, the 4 types of NoSQL. Let's look at the actual varieties. Let's do a rapid-fire breakdown of the 4 main types, starting with the key/value store. This is, without a doubt, the simplest NoSQL database out there. It stores data with zero schema, acting like a giant, super-fast associative array. Every single item is literally just a key tied directly to its value. And because it strips away all the complex overhead, it gives you incredibly efficient access times. You can clearly see how beautifully simple this mapping is. Key 1 points straight to value 1. Simple, right? But look at how flexible it gets. User 1's key points to an array of numbers, while user 6's key points to a value block that holds a name and an employee ID. There is no rigid table forcing every single entry to look identical. Total freedom. Next up, we level up slightly to document databases, or document stores. These still use that key system, but they pair the key with a much meatier data structure called a document. These are usually loosely structured sets of data in familiar formats like XML or JSON. The huge thing to remember here is that the database treats the entire document as a single whole unit. This approach is wildly popular right now. We're talking MongoDB powering GitHub or CouchDB running heavily behind the scenes at Apple. Check out how perfectly encapsulated the data is in this JSON example. You've got a unique object ID acting as the key, and bundled right inside the document is the content type, the author, the title, and the date. It's totally human-readable, highly flexible, and everything you could possibly want to know about that specific article is housed in one neat little package. Number 3 is the column-oriented store. Say goodbye to reading data row by row. Here, data is sorted and stored by columns, which are then grouped into column families. This means your data isn't trapped in one giant sluggish table. It is specifically built and optimized to run massive analytics over astronomically large datasets. If you've typed anything into a Google service today, you interacted with Google's big table. Scrolling through Facebook, you're pulling from HBase. That is the kind of mind-boggling scale we are dealing with here. What's genuinely crazy is how distinct user profiles can be when they exist side by side like this. Look at Bob, Brittany, and Tori. Bob has an email, a gender, and an age. Brittany has an email and gender, but she skipped the age. Tori? She has an email, but swapped out age and gender entirely for her country and hair color. Try pulling that off in a strict legacy database. It would be an absolute nightmare of empty cells and errors. But here, it's completely natural. And finally, we arrive at graph databases. If your data is highly interconnected like a giant web, this is your go-to. Everything is stored as a network of nodes, the edges connecting them, and the attributes for both. The magic trick here is that you can apply labels to everything. You use those labels to navigate and instantly untangle massively complex relationships, perfect for social networks or those freakishly accurate recommendation engines. Think about it like this cinema booking system. It's not a boring list of tickets. You have a person node connected to a booking node. That booking specifically connects to a seat, which is inside a row, inside a cinema. Meanwhile, the booking connects over to a specific session of a film, which the person node probably has a likes relationship with. It literally maps the messy, interconnected reality of our world. Well, we have covered an absolute ton of ground today, transitioning from the rigid rows and columns of yesterday's databases to the completely fluid, distributed, base-driven world of NoSQL. So I want to leave you with this thought as you go about your day. Knowing how the massive scale of the internet completely shattered the old rules, what kind of database do you think is running the apps on your phone right now? When you like a post, stream a track, or book a ride, which of these 4 NoSQL structures is firing away in the background? Thank you so much for joining me for this explainer. Keep learning, keep questioning, and I will catch you in the next one.